This video describes when a Moebius transformation is a conformal mapping. And the thing to realize is that the equation displayed on the screen here is what a Moebius transformation is. A, B, C, D are complex constants. A, B, C, and D are complex constants. Z is a complex number, complex variable. And recall, conformality of a complex function f if condition 1 f is analytic and secondly the derivative is non-zero. Okay, so what we need to do is we need to verify that this function f has got a derivative at various places and that it's non-zero. And it will be important to remember that this determinant-like quantity AD minus BC is not equal to 0 by assumption. All right, this is just a quotient rule situation. So computing the derivative for a Moebius transformation involves computing the derivative. And we've got the good old quotient rule in work. And a little bit of algebraic manipulation.
What? No copy?
And conveniently there's a cancellation. And that cancellation results in a quantity, and the thing to notice is that provided this is defined, it is definitely not 0. Provided that the denominator is non-zero, and by assumption AD minus BZ is not equal to 0 because it's a Moebius transformation. So what about this? CZ plus D is not equal to 0. That simply says that Z is not that quantity. It turns out actually in this very particular case it doesn't actually cause a problem. And this actually is best seen by graphics, but if you want to be safe, thus the Moebius transformation is conformal for all Z except Z equals minus D over C. And it turns out it's actually conformal there too, and you can see that graphically. Although this kind of analysis here doesn't show it. And that's fine. So to see that, let's have a look. On the left, this function here, this is the Riemann sphere, sort of the input coordinate. So we've got 0 at the bottom, and the point at infinity at the top. It's the Riemann sphere. And we have the image of the Riemann sphere, the image of a particular Moebius transformation, and as it happens, this point here, the way that I've chosen this one is 0, and there's the point at infinity, or at least the image of the point at infinity. This is the image of 0. And you can see that everywhere these lines of latitude and longitude do intersect perpendicularly. It's a good sign of conformality. And that also happens at the image of 0. Of course, our calculation indicates that's not a problem, but it also actually happens at the image of the point at infinity. So the place where we have the divide by zero turns out not to give a problem either. In any case, it's useful to think with this visualization of the structure of a Moebius transformation. It actually looks a bit like the electric field lines of force, and indeed that's no accident. As some of the other videos will show, this is something that happens in general, and this is because really analytic functions have everything to do with harmonic functions, i.e. solutions to Laplace's equation.